Hi guys, Dr. J here, and in this video I'm going to talk a little bit about Earth's magnetic field and how it gets generated. So if we look at the Earth, the interior of the Earth at a very large scale, this outer area is the whole circumference of the Earth, and then we have what's called the outer core. So this center part of the Earth is what we call the core. It's made almost entirely of liquid metal, so iron, nickel, some other things, and it's actually very large. So the total core of the Earth is about 4,300 miles all the way across, and that's actually about the same size as the whole planet of Mars. So you could just about stick Mars into the Earth's core and there would be an almost perfect fit. But it's made up of liquid metal in what's called the outer core, and the outer core is made of predominantly liquid iron, as well as I said, nickel and some other elements. The inner core is actually solid and probably very close to pure iron. So what we have in the outer core is it's actually liquid convection because it's liquid iron, and that convection induces electrical currents which induce magnetic fields. So we talked about this in some other modules. We have electrical currents that are induced because of eddy motion through a magnetic field. And those electrical currents produce the Earth's magnetic field. And I'll just draw this schematically as some loops of current. And again, this is best understanding. And those, as you know, a current traveling in a loop like this is going to induce a secondary magnetic field. And so that's what's thought to generate the Earth's magnetic field. Now, the magnetic field itself is a little bit inclined to the Earth's geographic North Pole. So if this is the geographic North Pole there, and then we have the magnetic poles, they're inclined to each other by about 11 degrees. Now, I'm modeling, in this case, I'm kind of modeling the Earth's magnetic field as a dipole, which is just like a bar magnet. In reality, it's a little more complicated than that. But to a first approximation, we can model it as a dipole. Most of the energy is in what's called the main dipole moment. Now, you might ask, well, how do we know all this stuff about the Earth's core? Obviously, we've never even come close to drilling that deep in the Earth. In fact, the Earth's crust is about the thickness of my marker line there. So how do we know all of this? Well, we actually know it because of earthquakes. So earthquakes happen, send out earthquake waves all through the Earth. And we can detect waves from earthquakes, and there's two types of earthquake waves, shear waves and compressional waves. Compressional waves can travel through any type of medium, solid, liquid, but shear waves can only travel through solids. They don't travel through liquids, and they certainly don't travel through gases. And we can actually see for a given earthquake, and sorry, this is getting a little messy now, but let me just draw this on there. So let's say we have an earthquake here, which is actually a little bit too deep. It should be more like up in the crust, but just so that you can see it a little bit better. And then earthquake waves travel out, compressional waves and shear waves, kind of travel through the Earth in these curved paths. And I'll just draw it in both directions here. And what we see, anywhere where we're on the close side of the Earth to that earthquake, so a seismic station over here, for example, will detect both compressional waves and shear waves. But if we have a station over here, this drawing might look a little funny, but basically what we see is that if we have a seismic station over here, we see the compressional waves, but there are no shear waves. And that tells us that there must be liquid at the Earth's core. And we can actually map out, using earthquakes all over the world and seismic stations all over the world, the approximate size and shape of the Earth's outer core. And so that is going to be liquid. Now, the reason we think there's an inner core is a couple of reasons. One is also because of seismic waves. You actually get seismic waves converting from shear waves to compressional waves and back and forth at boundaries. And we can measure those and determine that the Earth's inner core is likely to be solid. And there's also some pressure and temperature conditions that we can take into account that make that make sense. Okay, so now let's talk a little bit about how Earth's magnetic field interacts with the broader solar system. So one of the things that we know about the sun is that it's always putting out charged particles. It's emitting charged particles in the same way that it emits light. And so you have this stream of charged particles coming from the sun. Those are damaging particles, and in fact, it's thought that the reason that Mars does not have an atmosphere right now is because it's been stripped away by the solar wind from the sun. Now, the Earth does have a strong magnetic field, and so that interacts with these charged particles, right? So if you have charges and magnetic fields, those are going to interact together. And what happens is, again, close to the Earth, the Earth's magnetic field looks similar to a dipole, a magnet, or a magnet. But when we get farther away from the Earth, it begins interacting with these charged particles. The magnetic field kind of gets compressed on the sunward side, and then on the backward side, it actually streams away from the Earth. And you'll see a picture about this in a few minutes. This magnetic field, the Earth's magnetic field, is very, very important for protecting us from the solar radiation in the solar wind. As I said a second ago, it keeps the atmosphere from being taken away by the sun's solar wind. This is also the cause of the northern lights and southern lights, the aurora borealis. When these charged particles interact with the magnetic field, some of them get funneled into the Earth's magnetic south and north pole. So the Earth's magnetic field is very important. It is life-sustaining for the Earth. If we didn't have it, we would probably not exist. And it's also helpful and important for doing geomagnetic surveying. And so that's what we're going to do. So I wanted to show you a little bit more about how the Earth's magnetic field looks and how it works when we're measuring it. So just some nomenclature. We have geographic north, geographic east, and down. And this is how Earth's magnetic field is typically measured when we're out in the field. You can see the red vector there is pointing in the direction of the Earth's magnetic field at that particular location. And you can see it's not necessarily horizontal. And in fact, it won't be horizontal anywhere except for the Earth's magnetic equator. And you can also see that there's some difference between Earth's magnetic north and geographic north. And that's what we talked about. And here it's a little bit exaggerated, just so that you can see it. But the declination is the angle between the Earth's geographic north pole and the magnetic north pole. And the inclination is the difference between the horizontal plane locally and the vector direction of the actual vector pointing in the direction of the Earth's magnetic field, wherever you are. And the intensity, what's called the magnetic field's intensity, is just the magnitude of the vector at that location. And we've talked about in other videos, the Earth's intensity, the intensity of the magnetic field, can change from 25,000 to 65,000 nanotesla approximately as you go from the equator to the north or south magnetic poles. This site, which I will link on the Canvas webpage from the British Geological Survey, is a very nice website to learn a little bit more about the Earth's magnetic field. And again, they have some definitions, just essentially these are the same as these vectors over here with various different nomenclature. And they talk about magnetic observatories all over the world, as well as satellite measurements. Here's the horizontal intensity of the magnetic field, so the magnitude of the vector in the horizontal plane. And this is the vertical intensity. And as you can see, the vertical intensity is definitely the strongest at the poles. And here's another image just showing the Earth's magnetic intensity in a different way. Here's another picture from the Japanese Space Agency, just illustrating the Earth's magnetic field in space, as we were talking about. So you can see, again, the direction of the solar wind. You see the magnetic field lines and how they are getting kind of streaming out behind the Earth. And this is behind the Earth in respect to the sun. And then you can also see how as solar particles get trapped inside the Earth's magnetic field, that they would eventually make their way to the north or south pole, magnetic poles, and that's the cause of the aurora borealis. So that's about it for the Earth's magnetic field, and I will see you in the next video.